We're going to give everyone about 1 minute to just filter in.
All right, let's get started. So, hi everyone, welcome to the Youth AI Talk. We're very excited to have you here. Before introducing today's talk, I would like to give a brief overview of the Youth AI speaker series because we have quite a few new audience members here. So, for those who are new to Youth AI Lab and what we do, we are a youth-led nonprofit US organization dedicated to increasing student to expert connections, AI literacy, and making high school students future ready. This webinar is a part of our monthly speaker series. To raise awareness of AI among all communities, we invite experts from academia and industry to share their knowledge and discovery in specific areas of AI. Unlike other technical talks, these talks will be tailored to people without much background in AI. Therefore, they're fun to listen to and easy to follow. We hope that by listening to these talks regularly, you will gain a solid knowledge of AI. So please help us spread the word about the Youth AI Talks. Thank you so much for your support of this education and community service initiative. Please also consider visiting our website, youthay.org, and sign up to receive announcements for other upcoming events like this one. For those of us who miss our talks, feel free to also read the webinar summary that will be released after the talk. So we have hosted 16 fantastic talks since the kickoff of our speaker series, covering important areas of AI such as efficient AI, graphics AI, cognitive AI, finance AI, as well as different implications of AI. Our speakers are held in high regard to their respective fields, whether it be academia or in industry. We have speakers from big players in industry such as Facebook or Meta now, Microsoft, and speakers from top AI universities such as Carnegie Mellon, MIT, UC Berkeley, and Stanford. Replays of these talks are mostly available on the Youth AI YouTube channel, with the exceptions of a couple talks, which are not available on YouTube due to company policy. So, though our speaker series has been on hiatus for the past few months, during that time, we at Youth AI Lab were still active in collaborations and partnerships to create exciting opportunities for K-12 students who are still interested in AI. We're happy to be back with our speaker series and honored to kick off the continuation with words from Dr. Essa. And before we start the talk, our upcoming talk on August 20th is Bringing AI to Healthcare, featuring Dr. Leo Grady. Join us in Dr. Grady as he shares his experience and thoughts as an internationally recognized leader in bringing AI to healthcare. And the link to the Eventbrite for that should be in the chat soon.
Sounds good. Thank you, Hannah, for the introduction. And before introducing Dr. Essa, I'd like to briefly go over the logistics of the talk. Since we have an audience watching from our YouTube live stream, as well as on Zoom, we'll be doing Q&A through a platform called Slido. So you can either go to the URL that will be pasted in the chat momentarily, or go to Slido and enter event code 12356. So feel free to submit questions throughout the talk, but we'll only be answering questions in a Q&A session at the end of Dr. Essa's talk. So be sure to stay around for that one. Now to introduce today's speaker, Dr. Essa. Dr. Essa is a distinguished professor in the School of Interactive Computing, Senior Associate Dean in the College of Computing at the Georgia Institute of Technology. He serves as the inaugural executive director of the new Interdisciplinary Research Center for Machine Learning at Georgia Tech. And Dr. Essa is also a senior staff research scientist at Google Inc. and leads the research office in Google Atlanta. And his work spans the areas of computer vision, machine learning, computer graphics, computational perception, robotics, computer animation, and social computing, with potential impact on autonomous systems, video analysis, and production, human-computer interaction, AI, computational behavioral social sciences, and computational journalism research. He has published over 200 scholarly articles in leading journals and led conference venues on these topics as well. And he is well known for having coined the term computational journalism alongside his doctoral student in 2006. So today, our brilliant speaker, Dr. Essa, will discuss his experience in the field and discuss the meaning of machine learning, artificial intelligence, and computational journalism. So let's give a warm welcome to Dr. Essa. Thank you for joining us today.
Well, thank you so much, and thanks for inviting me out here. Let me see if I can make this technology work and share some slides with you.
Sounds good.
First, you may have to, okay, good. Let's see, I want to make sure not to share things that I'm not supposed to share with you folks, but find the right slides. Where did that go? See, where did it go? There we go. Give me 1 second.
And for those who are just joining us, welcome. Thank you for joining us this evening. Right now, we're just about to get started, and we'll have links for the Q&A pasted in the chat.
All right, you see something?
Yes, we do.
Okay, and you still see something?
Yes, we do.
Okay, good. So thanks again for inviting me out. It's a pleasure to be actually with a group of people who are excited about the area of AI, machine learning, and such. It's always, of course, kind of odd when you're giving a talk to a screen in front of you. And I know we're in a new era of our lives where I'm now sitting in my basement. Without any natural light, with all these types of light sources in front of me, lit by a monitor in front of me, trying to give you a sense of how exciting the disciplines of machine learning, AI, and such are, without actually seeing you. Now, having said that, technology we're talking about is facilitating some of the stuff that we're talking about too. So that at least is positive. So what I'd like to do today is give you a little bit of sense of who I am, and also a little bit of what I work on, and also a little bit of a sense of how I got there. Now, what I would have loved to have done today, and maybe that's what we will get to in a question and answer session types of things, is learn from you as to what excites you. To me, the classroom is something I spend a lot of time in. And to me, a classroom is something where we engage with students much more directly and let them ask questions. The Socratic method of learning, where basically everything is driven by both experiential learning and also engaging directly, is where the fun is. And hopefully more tools like that will be developed to support that as we live in this kind of a distributed world that we're in. Now, having said that, the distributed world has allowed us to have these types of conversations, even though all of you are in different parts of the country or world right now. So let's kind of take in, of course, I do find it interesting that we're all doing this. We must be really dedicated to this on a late afternoon or a Friday afternoon like we are. Let me make sure, okay. So first, let me give you a sense of who I am, especially, so what I understand and looking at your website and stuff, I'm talking to a group of upcoming, young, exciting, potential future developers, innovators in the area of many things, including, AI and machine learning. So, I'm of course, relatively old now, most likely the oldest person in the room. But, just like you, I was in high school or middle school many years ago. I was born in Pakistan and immigrated many years ago. My family has been spending a lot of time in the US since the 70s and 80s. So I've been around in the States for a long time. I will admit that when I was in high school, I had no idea what AI was. I had no idea what even actually initial computing types of technologies were. I was interested in math and sciences and a whole lot of things around design and stuff like that. I was interested in modern technologies, but of course, in those days, we didn't have a good sense of what computing technology, far less what AI was. But of course, I come from privilege because I was able to kind of go to some of the best schools, engage with the right kinds of people, and have the benefit of learning from some amazing people. After my undergrad in engineering and sciences, I was at MIT for a while, where I did my both master's and PhD. And I also spent time there as a research faculty before I moved to Georgia Tech. And the only thing I was correct is that, when you mention the top universities that work with computer science, make sure to add Georgia Tech because we are a top university in computer science, AI, and machine learning right now. And we have many colleagues at some of the other schools that you mentioned. From my college years, I did become a professor at Georgia Tech, and I have been professor for over 25 years now. And about 10, 12 years ago, I also joined Google to work on various types of research projects and stuff like that. And some of them I'll try to mention in the next short bit to kind of give you a sense of what kind of stuff we work on. But bottom line is, I'm interested in creating new technology. And more importantly, also, I'm interested in working with the next generation of people who will create this technology. And that's what a professor does. We kind of work very closely with our students. We train them, and most of the time, while we are giving them the basics and foundations of what they want to learn, they're actually teaching us a whole lot about what's new and exciting and their way of thinking through things. So that's why it's kind of a symbiotic relationship we have with our students. And I'm very proud of all of the students I've worked with over years that have gone on to do amazing, exciting things. I also wanted to add that, sometimes we also know that what we want to do. Now, I can tell you when I was in high school, I had no idea what I was doing. All I wanted to do was go play sports. Slowly and slowly, I started getting into education types of things and grades and stuff. When I was in college, when I was doing work in different types of things, I had no idea if I wanted to be a professor. Somehow or the other, these things started happening. So sometimes you can plan these things. There's nothing wrong with that. Sometimes they just happen. Okay. So things I work on. I primarily work on an area called computer vision. I'll tell you a little bit more about what computer vision is. You are all, of course, aware of what AI is. We'll talk a little bit about AI machine learning also today. I also work on robotics. And some of the things were already mentioned. I also work on computer graphics. So while computer vision is about the process of understanding what images are, computer graphics is about the whole process of making those images. I also work on human-computer interaction, and we'll talk a little bit what computational journalism is in a bit too. But I'll tell you a little bit of the vision or the thought process that I have with the kind of work we do. So imagine, these days we have these computers that are quite aware of what you're in, how you interact with them. But if you were to just think about the early days of how we interacted with computers, and we kind of have the story that, let's imagine, science fiction wise, there was some sort of apocalypse and the entire, 500 million years from now, somebody came to the planet Earth, some alien race, and they came in and they started kind of doing studies of what kind of society lived on this planet. So think through a little bit of Star Trek types of things, right? And if they were to kind of start analyzing and they came and looked at, let's say, for example, found computers, they would imagine that humans, unless they found, of course, remains of us and stuff like that, would have had 52 fingers and would have no things like eyes or ears and stuff, because that's how we interact with computers, with a keyboard, right? Touch them in different possible ways, have coded languages and stuff like that. There's no evidence that we actually speak to our computers. There is no evidence that these computers can see us. But that's the kind of stuff that actually is changing. Computer vision is about giving machines and computers an ability to see and interact with us pretty much at the same level as we interact with each other. Similarly, computers give, technologies has now given computers an ability to hear, interact with us, and of course, they can also respond to us. So all of these disciplines that I'm talking about, computer vision, the charge of actually building machines that can see at the same level as humans do, AI, machines that would actually use those technologies to be able to understand the environment they're in. Machine learning, again, use the information around themselves to be able to then kind of react to various types of things, make decisions. Robotics gets further down into the space of trying to kind of say is, okay, how would these computers perhaps even have embodiments? Maybe look like humans or look like, R2D2 types of robots and stuff. Computer graphics then goes into saying is how can we synthesize those types of environments? This gets into virtual worlds, but all that kind of stuff of trying to generate much better technologies around it. Then, of course, is this whole concept of how do you build human-computer interaction? How do you make it effective that humans and computers can interact with each other in a seamless manner? So now all of this kind of says is the computers, we had always this thought of the computers, the best way to interact them was with a mouse and a keyboard. Well, that's something that needs to change to much more interactive interactions. So these days, for example, everybody, you all know this, is we can pick up our phone and talk to it. We can do things like, hey, Siri, do this, Google, do this, Alexa, do this. That's kind of basically much more conversational, speech-driven stuff. By the way, those are artifacts of work that AI has resulted in. AI is partly involved with all of this recognition world on trying to do speech. Similarly, these days, the computers can recognize and give you access to your phone by recognizing your face. That's computer vision. What's behind all of this is various forms of pattern recognition data analysis that's coming through AI and machine learning. And of course, robotics and types of things can provide other context. So far, I've ignored the term computational journalism. We'll get to that in a bit too. Just to give a little bit more specifics, and I think this was described in my introduction a little bit, but I wanted to give you a little bit sense of the core of the research my team works on. And again, I'm emphasizing my team works on is because my job is to recruit the best and the brightest who come and join my team, who can then engage in this kind of research that would then be taken to develop the newer forms of technology. So one of the major areas my team works on is understanding of video. I'll show you a little bit examples of that kind of stuff. And what that means within that is I'm interested in video. Now, what's the difference between video and images? Well, some people say video is nothing else but a sequence of images stacked together. And by the way, you folks are all part of a generation that's using video a lot more than any other generation in the past has. Some of you can start using your wonderful tools and stuff like that that are available to you in Zoom. And, all of you are, I don't know how many of you are TikTok users. Everybody likes TikTok? I must admit, I'm too old to use TikTok. I don't understand how to use it. But YouTube is another domain. So video has become a predominant source of interaction these days of various types of things, and also understanding things. You go these days, in fact, the funny part is, in the old days, when you got a new technology, you opened up the manual and you read it. Now what you do is, even that manual has nothing else but a link to a YouTube site. And you watch a video how to use it. If you want to learn how to cook something, you go to YouTube, you download the video, you watch the video, and that's how you watch and create these types of things. My team actually works on both analysis and understanding of that kind of video and how do you create it. Similarly, another thing we can do with it is, what is happening in an environment? As I talked about is, we want to build systems that are aware of the environment they're in. Well, that gets into understanding what is happening in the environment. How can we model what's happening? How can we predict what's happening? How can we analyze what's happening? Now, this can start kind of telling you a little bit more. Of course, the biggest potentially commercial application of AI that everybody talks about these days is autonomous driving, right? Autonomous driving is an example where a car is out there on a dynamic environment, a street. It has various types of sensors. One of them is a camera. There are other sensors on it. They're all temporally varying signals coming in through those signals. And what we're asking questions is, what is happening? The car is moving on a street, and it's also doing things like understanding and predicting where other cars are, and also understanding and predicting where people are. So of course, it doesn't hurt them. So that's kind of, again, understanding the behaviors and stuff like that. Autonomous driving is an example of it, but it could also be health related. Can we watch people moving around? Can we actually understand from their behaviors? Are they going to fall? Or are they going to hurt themselves? Or are they going to be able to kind of safely navigate in an environment they're in? Many different types of examples come from that. Then we work on action modeling. That is, if we were to kind of create these types of dynamic systems and understand them, well, even a car has to now move and act in that environment in a safe manner. We want to build robots. It has to learn how to kind of do different types of things. So, and then, some of the examples you see out there is you see the skating example. By the way, the skating example is work we did that runs on YouTube that basically improve the quality of video by stabilizing it. That is that because of the fact these days is we all have these mobile cameras, like the one I'm holding, my phone, and we walk around with them, they're shaking, right? How do you get rid of that shake? Well, that's that system that's been used by millions of people. Next, you see this example of a person playing a chess game with a robot. The robot is understanding the moves and moving the chess pieces in an approximate manner, similar to what a human would do. Of course, this robot does not look like a human. So that comes up is how do you do that different kinds of processing? Then there is this example you see again about, basketball case. In this case, we actually built a system that would look at videos of basketball and understand and predict what's going to happen before it happens. This one actually was looking at the whole tracking of people over a game of video, understanding the group behaviors and predicting things like, oh, where is a person going to be and how are they going to shoot? What kinds of shot are they going to take? This is kind of the intelligence of understanding what's going on. Then there's an example, and I'm showing you an example of computational journalism in social media. That was, how do you actually look at information? And how do you analyze information to improve the quality of information available to us? Again, bookmark that. We'll come back to that in a few minutes. We'll talk more about this kind of stuff. So this is kind of stuff we do. And I just wanted to kind of show you the kinds of work my team does. It's, of course, video analysis. We work a lot on tracking people in those videos, tracking objects, recognizing activities. We also work a lot more on motion understanding, analysis, and a whole lot of other kinds of buzzwords. This basically is a wordle of looking at a bunch of papers my team has written and what are the most common words and justifies the work that I work on video. Let's get into a couple of terminology issues here, because one of the things that's happening these days is there's a lot of confusion around what is AI, what is machine learning, what is data science, what is every other different types of things that is out there. Now, I know you folks are aware of what AI is, but we will still a little bit talk about that just because I want to, try to kind of explain to you at least my perspective of what AI is. These days, the word AI is being overused. In fact, sometimes I look at, there's of course now, as you know, a domain name with .ai. And I basically joke around that many companies out there with the name .ai as a domain name, the only AI is that domain name .ai. There's a lot of hype associated with AI. There's a lot of confusion as to what's going on. But having said that, to some extent, it's really good that AI is actually a much more common term. I can tell you, going back to the history, when I was a graduate student working in AI, and I'm sitting in an airplane going somewhere, and I would sit next to a person, and this person would, want to start a conversation with me, ask me, "What is AI? Or what are you working on?" And I would say, "I work on AI," and they would look at me as like, "What kind of an animal are you?" Nowadays, of course, I sit in an airplane and I say, "Oh, I work on AI," and they're like, "Wow, that's great." Of course, two things happen of it. One, they're impressed, and the second one is, "Oh, you're building Terminator or Skynet." So there's a scare associated with it. We'll talk about that too. But let's get into some of the basics of the concepts here, and then we'll build on that one to understand what's going on. First and foremost, the word intelligence is key in the word of AI, right? And again, I had the privilege of being at MIT and working very closely, not very closely, but being engaged a lot with people like Marvin Minsky, one of the people who coined the term AI. And again, the term artificial is very tricky in that concept, right? They were really interested in kind of developing a completely artificial machine-based system that would have intelligence similar to that of a human. And I know when the conversations began, they were thinking of many other terms. I mean, one of the terms I like is augmented intelligence, because that kind of leaves the agency not just entirely in the hands of a embodiment, a machine, but perhaps provides intelligence to a human at the same time. Or there are different types of other things that can be anticipation and intelligence associated with it. I think it was mentioned that there is a whole lot of other words associated with cognitive sciences and stuff like that. And those terms are all important that kind of come in. So, we can actually think about cognition. I also believe in perceptive intelligence that's driven by understanding and perceiving the environment you're around it, reacting, supporting to it. adapting to what kind of things are there. But intelligence is the key. And partly what excites me about the work in AI is it also challenges us to understand the term intelligence at its core, and also tells us that we need to understand what is intelligence, not just in a machine, but also in us humans. How do we learn things? How do we do things like, as within the age of 1 year, we learn enough motor skills to be able to walk, something we take for granted. How do we do that kind of stuff? Remember, I talked about how I want robots to be able to move, showed an example of how a robot could move chess pieces. Well, the question comes up is how can we actually have that kind of stuff happen that, as kids, we were able to pick up things and move them around. Nobody sat down and told us how to do it. It was much more of a natural phenomenon. How do you do it? And that's what I think is key about the research area we're in. So as I said, the history of AI starts off with people like Marvin Minsky and John McCarthy from Stanford. Minsky was at MIT, and other people like, Noel Simon and Papert and Winston and many others from that era got together. And actually there was a meeting in 1956 in Dartmouth where they actually coined the term AI. And again, there were other terms that they were thinking about, but in that instance, 1956, and you have to remember, 1956 is the early days. Just to give you a context, I started working with computers when I was in high school, but then I, joined my undergraduate degree program. And when I started programming, I was one of the first classes in my year that actually programmed using a keyboard. The year before, they were using punch cards. So this is how different things were at that time. And this is even before, right? This is 30 years before my time as an undergraduate student. So 30 years before, they were thinking about it. But these were amazing people. They were thinking about computers and machines. For example, whenever Bush wrote this article, As We May Think, this is trying to understanding how we think, what would be the future be. Everybody knows the name Alan Turing. He designed the Turing test while he was doing other things in that technology area to understand what concept of intelligence we think about. Lick Leiter in 1960s talked about man-computer symbiosis, the symbiotic relationship between a person and a computer. I mean, this is early concepts. I was at MIT Media Lab. Nicholas Negroponte was the director. Again, in 1967, he talked about this concept of an intelligent agent. How would we build these things that are aware, intelligent, and responsive? So this is as old as a concept there is. And some people ask the question, what is artificial intelligence? It's basically an attempt at building intelligence that is demonstrated by machines. It actually is about building intelligent agents that perceives the environment and takes actions that maximizes its chances of successfully achieving its goals. Now, by the way, in the world of robots, this would be actions that would be physical. In the case of internet, these actions will not be physical. These would be, synthetic actions and stuff like that, because these agents don't have to always have a physical rendition. They could have different types of renditions too. So very general term, but there, as I said, there are lots of additional terms we want to also think about. Another term, and by the way, I'm mentioning these is because, among other things, I teach classes on this one, and I try to emphasize the different types of things that come in. Now, earliest definitions of machine learning basically kind of came in to say was, it's trying to understand from any kind of data. By the way, data could be real data as we think about, or it could be sensory data. And now, once we know what that data is and how a system responds to it, we can encode that representation of input and output directly from the data. That basically means is I do not have to go write a program explicitly says, if this happens, do that. I'm basically building an automatic model that basically says is I'm going to train on this type of input to train that output. And next time I ever see anything that looks like this input is going to result in an output like this. So again, as you may or may not know about this, and I think you've seen enough talks on it, it depends on how I train it. Because I could train it on bad data and it's always going to give you a bad answer. Or I could just train it on a subset of data. It's going to be great for that subset of data only. It will not do anything for any data that's outside of that subset of data. So there are limitations what it could do, but it can scale very well. You could train it You can define many different types of ways of training it, and how would you actually build on this kind of stuff. For those of you, I know some of you haven't gone into, maybe you've done now a little bit of linear algebra. One of the first things we do in this kind of stuff is something called function approximation, or even regression. Regression is basically something like, well, I have a set of data points, and now I want to build a model that fits this data points. And now next time, if I want to actually ever extract anything, I will basically figure out is how do I project this on a data point related to the model I built. This could be done by things like regression or curve fitting. Again, something which you will learn about if you haven't already. But the bottom line is, this is learning from input and output in data itself, rather than explicitly writing code to doing it. The strength of this, of course, is obvious. We can actually do a whole lot of different types of things with them. Another types of things that I'll kind of emphasize in this one is, the whole field that's been existing for a while is, pattern recognition. That is, how do you actually look for patterns? And how do you actually look for those patterns and look for regularities and irregularities? This actually is also a strong and important part of it. It's a subset these days of pattern recognition, machine learning types of fields that is looking for data and understanding from it. And this could be done supervised or unsupervised. And ML is one of those approaches in pattern recognition, but there could be other types of things. You could actually build handcrafted rules. And that was how things began in the early days of machine learning, that you would actually define a set of handcrafted rules, and you would use that to kind of look for specific patterns. Another term that's used a lot these days is the term called data science. And data science kind of builds on from terms like computer science, but also kind of connects a lot with math, but also has a lot of specific examples from much more general broad search terms. It's a much broader term, and actually it's widely used these days. And it's an important term, and actually some people arguably also say that it's got strong roots in machine learning and computer science. Bottom line with all of this is, there is, these days, if you were to go into Google and type in machine learning data science and look for it, you will find that there are many different people that are saying is, oh, what is machine learning? What is data science? And you will see all of these wonderful diagrams that kind of explain to you what is the relationship with one or the other. My recommendation to all of you is start ignoring it. They're all extremely valuable. They're extremely important. And it doesn't matter what you call them. It's more important is what you use it for. And that's something I want to kind of emphasize more and more is how do you do it? So to me, AI is like a moonshot. It's like going to the moon. Machine learning is the fuel that actually is now showing a lot of value in trying to build that kind of system. How do you actually give it the fuel to get us towards the goal of AI? And data science might be the rocket ship which is going to use that fuel. So all of them are important. And these days, you have to understand is where you're going to get this knowledge. Of course, data science is important for business. Machine learning is the grounded tool that supports business. And AI is actually something which is getting into the inference mechanisms to support it. Also, I'll give you a sense of what computer vision is. Again, it kind of has a strong root in AI, but it's a basic field that attempts to understand how humans see different types of things. So as humans, we walk around and we see a scene and we can start categorizing things. An example here is I can look at this example of an image. If I was walking out on the street, I would know, of course, this is an elephant because I've seen an elephant. I would actually see a person. I would actually be able to categorize different types of things, parts of the elephant, a trunk or a tusk. I would see other things. I would also see that, oh, this is on the ground. And I would also extract all kinds of additional things, the color of the scene, red shirt, all that kind of stuff. This is something we take for granted. We want machines to have the same ability. Not the best example for it, but if there was a car, I would want the car to know its location, its orientation, what parts it has, if there's a person in it, which direction it's moving, and also how far it is from me, so I would not hit it, and also how far it's going to move in a few seconds from now. All of those types of things are, again, what computer vision, just from understanding images, is trying to do. By the way, computer vision, not autonomous driving, is not the only example we work on. Computer vision is used extensively in the medical domain to understand medical images and stuff like that, and can be used for diagnostic purposes of medicine and stuff too. Now, I've been kind of talking a lot about computational journalism, but I haven't told you anything about it yet. So let's talk a little bit about it. Before we talk about computational journalism, let me actually tell you a little bit about another discipline that I did not mention today, and that's called computational photography. Computational photography is a subpart of, let's say, computer graphics and computer vision. It's the process where we want to understand how photography, just as a note, photography is the whole process workflow of capturing light into a sensor and then printing that out or showcasing that light in different ways and using it for different types of purposes. The physics of how a light is captured is part of computational photography, or photography in general. What has happened in the last many decades is the entire process, how this light is captured, and then what we do with it, is become kind of extremely different because of how computational processes have been embedded in all aspects of it. What I mean by that is, of course, the sensor is no longer film. It's not a chemical object, but it's a digital sensor on how light is captured. That, of course, as it's digital sensors, has something to do with computation. We can move the lenses around. That's how light is collected onto the sensor. Pretty much like we do with our eyes, right? We move our eyes and our eyes blink and our eyes facade move around and stuff like that. That's also nowadays completely controlled by different types of computation. We can also kind of change how we see the light and how the light is controlled. That also is controlled by computation. So the entire process of how light is gathered, shared, and collected to generate a photograph, the entire workflow has now computation embedded in it, and the entire process is digital. So that's basically a simple, relatively simple definition of computational photography. By the way, if anybody's interested, I teach a class on computational photography. It's a graduate level class. Most of the videos are available on YouTube. I also teach a class on computer vision. Most of their content is also available. The content is available for free, of course. To get credit for it, you have to register with Georgia Tech. So why am I saying computational photography? Well, take the term light and replace it by information for the purposes of journalism, and that is the field of computational journalism. That is, now we're trying to understand is how is information gathered. Similarly, remember I talked about how light is captured, but how information is gathered, how information is distributed, how it is organized, how it is parsed, understood. Remember, in the case of photography, after we collect the image, we can actually figure out, oh, these pixels belong to a person's face. These pixels belong to a background. These days, as you know, most of your handheld phones can focus differently if they know face versus if they know the background. So now take that concept of pixels and light and replace it by information. We want to categorize, gather information, understand it as much as possible, the entire process of how it's captured, how it's organized, extracting information from it, how it's shared. One of the beautiful things about photography these days, you share photographs, right? I mean, you put them on Google Photos or something like that. I mean, we talked a little bit about TikTok. Again, we take videos and we share them. Well, that whole process is not limited to pixels and light, but to information. And as a whole, how do you take that information and put in the context of citizenry and journalism? That's what computational journalism is. And of course, just like the verifiability of an image is important, even more important that we actually work on verifiable, authoritative information from journal sources. So that was basically the premise of this whole concept of computational journalism, is taking how computation has now embedded itself in all aspects of how information is gathered, shared, and distributed, and how do you make sure it's verifiable and accurate. So, journalism is really about verifiable, accurate information for citizenry and decisions. How does computation support it? And this partly is important because nowadays the entire pipeline has changed because how we gather information, how we distribute it. In the old days, the information was gathered by journalists going out there, and then writing reports. But these days, I mean, they can be there, or citizens can be there and start tweeting information. The channels are much different. How you can actually extract and understand information much different than it was before. So I think that's the whole part of what has changed, and that's what I mean by computational journalism. I wanted to actually, before we go on, I wanted to kind of point out that there are certain challenges these days that we have to understand. This is actually a paper that was written in 1966. Remember, I showed you the history of AI. This was actually a project written up in 1966. This was referred to as a summer project. People sometimes, even the most amazingly bright people, find some problems. They find them to be easy or hard. This was written up as an internship project that computer vision will be something they will work on for one summer and make a whole lot of progress on it. 1966, we're still working on solving computer vision many years later. Okay, so that's how some of these problems are hard. AI was also something we thought we were going to actually make it work in the 60s and 70s. Some things work. You can pick up your phone and you can talk to it. And you can actually be more intelligent because you can pick up your phone, and doesn't matter anywhere you are, as long as you have network access, you can find out things like, what's the weather? You can ask it things like, oh, what is the height of the American president today? What, what is their favorite color? This is the kind of stuff that you didn't need to know, but now at that moment, if you needed to know it, you could find out. You could find out, oh, I want to, what's the name of the actor in the TV show Miss Marvel? Something you didn't know, but now you actually have that kind of knowledge and availability to you at your fingertips. That's what actually we can do. So there are things that work, there are things that don't, but that's the kind of challenge. So this is just to kind of give you, and I'm not going to go through this, but people are, of course, talking about how valuable AI and machine learning is. It's changing the business world. It's changing every possible thing on how we work with different types of things. I'm going to skip over this just to kind of give you a little bit of a sense of what AI machine learning has. There are 5 different camps in machine learning AI that have kind of also shown us a little bit of how things have changed over time. These are referred to as symbolists, evolutionaries, analyzers, Bayesians, and connectionists. Just to kind of briefly talk about it, is that symbolists were basically using a lot of initial information or knowledge, higher level knowledge, with data to make inferences. This was some of the earliest days of AI. Start off with knowledge and build rules based on this one that would make inferences. Then basically people started saying is, okay, this doesn't scale. Let's start kind of understanding how the human brain works. And that got us into understanding neural connections, rather connectionist large models, and using that to understand how knowledge goes through a network to understand information. Then came all of this kind of stuff around genetic algorithms. Can you actually understand how different types of processes evolve in nature, and can we use that to learn different types of things? Then came this whole other word of Bayesians, which basically started getting things to be more statistical. Looked at statistical evidence, incorporated that into understanding about more of the phenomenon or what's going on. Finally, there was another bit of work which basically said, okay, let's look for analogies. If I can actually model one phenomenon that's similar, can we use that to find other similarities between it? This led to work like support vector machines and nearest neighbors. The reason I'm kind of pointing this out is these kind of go through different phases. We started off all of the earliest works in AI by doing work on symbolists and connectionist types of things. Then came areas like evolutionaries and knowledges and Bayesians. Right now, you must be hearing a lot of works around what is called deep networks. Well, that's entirely going back to kind of connectionists more and more, but we are now continuing to use the Bayesian models of statistics to support it. We're also leveraging a lot of symbolists where knowledge associated with how things happen is being used, but we're also kind of understanding how different types of similarities are modeled. This is just to kind of give you one technical nugget to think about it. I can share with you, the slide deck will be there and has a whole lot of additional stuff on it. I'm going to skip this too, which kind of gives you a sense of what is different about the business. But the 3 C's that I kind of want to mention is, what is important in this era of computing? Well, of course, we have a lot more computing, right? At the edge, as I said, I have a cell phone in my hand right now that actually has more compute power, as you've known by yourself by now, than what was used to send the Apollo missions to the moon. We have a lot of power right at our fingertips. Of course, there's a lot of other stuff up there. We also have a large cloud, right? We can put things on the cloud. I mean, you've heard many things around it, which actually gives you a lot more strength of computing, both at the edge and then the cloud and the network within it. But then also what we have is the crowd. And that is what the social computing phenomenon is, right? We're very willing to kind of work with different types of things and help each other out. I mean, so you've heard about the concept of wisdom of crowds. I mean, the whole Wikipedia was, very citizen-based. People went in and actually updated information, provided correct information, and the crowd start kind of giving you more data and correct authenticated data. So those types of 3 main things are extremely important in the current, and those would be the few reasons we've made some huge progress in where we are. I'll move through this, but this session kind of pictorially shows that this is the kind of what's going on. I mean, edge, smartphones, computers, and stuff like that have changed the paradigm. I mean, just to give an example, early 1900s, an operating theater looked like that. Now the operating theater looks like this whole like jet age, displays and computers and everything else. A lot more compute power right at this place where we need it. Then, of course, there's cloud. We know all of this kind of cloud stuff is going on. We can put things anywhere, everywhere, and access it from anywhere. And crowd, as I said, adds a new dimension, because all of a sudden we have a lot more information, but the crowd is now, since they're connected by the network, can provide a lot of information about what's going on. And the reason I'm mentioning is this is where also it connects back to computational journalism, because social networking, collection of information, how do we kind of have different types of information that's going on? I always refer to is that because of the availability of cameras, again, remember, I'm interested in cameras, we can see anything and everywhere, anything from everywhere, right? I can be sitting here and I want to see what's happening in Australia. There might be a lot of cameras from there that are going on. These days, any event happens, there's a video of that available because somebody has popped up their edge phone and captured it. So then, of course, we also have tools like Mechanical Turk, where people are willing to annotate information, correct information, provide information, stuff like that. One of the biggest movements that changed the world of computer vision was this Imagenet, where people took large amounts of images and used that to understand more about scenes. And of course, these were also annotated. People took pictures of their cats and said, what kind of cat was it? So we therefore have a really good cat detector. We know that same thing about faces and stuff like that. Competitions are coming in for this stuff. Having said that, of course, we have to be very careful with different types of things. Data is very much important. Of course, people have used words like data is the new oil, it's a valued commodity. But then I also want to warn is there is a challenge with data. As remember when I said earlier, I give it data, I learn from this data, and now I can model phenomenon. And anything that I can look at in that data can be modeled. So anything I test that is within that data, it'll do very well with. What happens if I now test on data that was not something I would train on? Of course, it would not do well. So we have to constantly adapt our training to testing. And that's something we want to kind of get into. An example of this we've seen is with face data, face recognition, stuff like that, where we basically don't do very well. I like to always bring up this term here, and this has been kind of something which I always think a lot about, that these days we are in a stage of a lot of hype and excitement and hype on AI. And then, of course, many people are also telling us the fears of AI, right? Terminator, Skynet, and all that kind of stuff, all justified. We have to be very careful with them. But this statement tells me is one thing which I'm extremely, I believe in, that we always tend to overestimate the effect of technology on the short term, which basically means right now we're looking at everything and we're excited about it and we're saying it's going to solve all the problems. We're overestimating what it can do. but then we underestimated the effect of it on the long run. So right now, when we're talking about it, and then after we said, oh, it'll never work, but then I remind people, speech recognition works. Most of the other types of things, there are medical devices that have built-in AI that monitor and track our behaviors and tell us what's going on. That was something developed almost 15 to 10 years ago, and that's practical and available. So I think, we have to understand how to kind of leverage that concept. And of course, I also want to say computers are far from perfect. And of course, humans are far from perfect. I always use this example. So as you know, my name is Irfan and last name is Essa. When I'm typing or anybody types in on an system, it autocorrects, the computer autocorrects this to Oregon or urban. Okay. But the funny part is, whenever I ask and tell everybody my name, humans always misspell my first name, Irfan, to Ifran. And I think it is because people are very good at typing words if and ran. So just to give you an example, there are many differences between how machines work and we work. And this is an example, at least this one simple example, that there are many differences in how we also make mistakes. And we have to kind of start understanding what they are. I actually do have a lot more slides and stuff like that, but one of the things I wanted to do was engage in at least some sort of conversation with all of you. So with that, I'm going to basically end, but I want to, before we go on, one thing I want to make sure is we also understand that these systems are not perfect. These systems need to be developed with a lot of thought and care for doing machine learning, AI, computer vision, and stuff like that. I always give example that I think anytime now we write code, any one of us, we have to start thinking about the impact of what that code would be. And take an example, right? Humanity has been working on technology for ages. Many groups of people work together to design and build a building. And they put in a lot of safety protocols. They go through various types of codes. There is an oversight committee that looks at it and says, oh yeah, this is approved. You can build this building. Dozens and hundreds of engineers work on cars. They're designed perfection. There are errors that they model, they kind of understand and are responsible for what things it could or could not do. Those were all efforts that took a lot of people many years to do. But right now, you would all agree with me is that you can go to your basement or nearest coffee shop, open up your laptop, go to a website and write code on a Colab on a browser, develop something. If it's useful, you can then actually upload it to some app store, and somebody can then download that on an app store and start playing around with it. So the bar to actually develop things that people use has gotten really low. That comes down to the simple fact is we need to be very careful on what we develop and distribute, because sometimes, of course, they might be used incorrectly for the purposes that they were designed for, or they might not actually use, if this was a machine learning AI system, train it on the right data and use it for something incorrect. Now, of course, again, the same example of how computers and machines do it different. I always use the example of images. So you may know that photography has had this issue that most cameras, even in the early days of simple photography where they were doing the dark room photography, they developed technologies that would actually make faces look brighter. And most of the initial work was done using models that were, of course, people with much fairer skin. So that would do a really good job of, and this was chemical processes, by the way, this is not digital photography. Chemical processes, and there are some things called the Claire charts and stuff like that. What basically was being done was using those things, they were enhancing the quality of pictures. And of course, they were designed, but majority of the people, remember the numbers, were fair-skinned. But of course, when you applied the same kinds of stuff, even with chemical stuff, for dark-skinned people, or people with skin, color, people of color, they made their skin look brighter, not the intended output. The same thing is true with digital photography. Some of the initial models that were built were all built, and again, they were built with different types of people of fair skins. Dark-skinned people were not represented as well in that data collection, and therefore, it resulted in biased analysis. My PhD topic was in the area of face recognition and facial expression recognition. When I did this PhD work, my initial data collection was all of my peers that were in my lab, which were all, graduate students. Not a lot of people with color, but of color. So much it's worked really well for 20-year-old males. It did not have a lot of data of any other types of things. So I have to just in that instance also remind people that it works only for this data set. And it works well for that data set. It has not been tested for a larger variety of different age groups, different skin colors, different types of other demographics. So again, these types of systems, you have to think through and be responsible as to what it's capable of and what are the risks associated with it doing something wrong. With that, I'm going to basically stop and see if you folks have any questions.
Sounds good. Thank you, Dr. Essa, for the fantastic and comprehensive talk. I think really some deep insights into these terms that are often discussed in the field of AI. And a lot of important insight was covered. I personally really enjoyed when you actually mentioned machine learning is the fuel, data science is the rocket that'll use that fuel. I thought that was kind of a mic drop. And so I know we all wanted some engagement, and I'm sure our audience has plenty of questions. So we're going to head over to a Q&A session with Dr. Essa. And so for those who might have missed the link, we're going to paste the link to the Slido below in the Zoom chat. So of course, feel free to ask any questions you want Dr. Essa to answer there.
Now, will one of you be the persons to transcribe those questions, or will I see them? Okay.
Hannah and I will both ask you them back and forth. And of course, we also have our own questions as well.
Okay.
But definitely, thank you.
I'm going to end the slideshow.
Sounds good. Okay. I suppose now let's first head over to questions on Slido. We have someone asking if you would be able to give an example of computational journalism.
Sure, dozens of examples could come up, but I can give you one that is really kind of something really, so for example, these days, breaking news is much more instantaneous, right? And sometimes that breaking news, because of the rush to get the information out, may not be correct. So for example, I was sitting there and but this is an instance from 10 years ago. I was actually sitting at a well-known journalism organization, meeting with everybody else. And while we were sitting there, there was I'm not talking about the recent Supreme Court decision. There was a Supreme Court decision that initially got leaked. And the first part was misinformation. Somebody leaked the wrong one. The entire journalism organization I was with jumped to at that point and went towards getting this out to publish, because the timeline of trying to do this was there. But having said that, as soon as they started moving it, the other types of the social network got active and started kind of saying nope, this is not true, this is not true, this is not true. And that verified the information really quickly. So that's one example. And I'll give you another example of this type of stuff, right? Let's say, and I'm going to specifically talking about misinformation because that's something I think a lot about these days. These days, there's a lot of misinformation that people post an image. And by the way, this has actually caused riots and property and life damage in different parts of the world, is where somebody posted an image and didn't change the picture at all, and just changed the tagline saying and these were basically an image of people doing some sort of a religious practice and laying down. People took that image and basically said, this community caused violence and there were people hurt. This picture did not show anything like that, but they just changed the caption, and this went on WhatsApp to an entire society, to the extent that people got so angry, went to the town square and started rioting, until somebody had to kind of walk in the context and say, oh, by the way, this is all fake. There's no truth here. So this is an example of computational journalism where, while on the good side is this information can break very quickly, the problem is people can use this kind of misinformation But now how do you use computational journalism types of principles to bring it and kind of start saying is, no, let's verify this information first. So that's one example. The second types of things is you can see these days, if you go to any kinds of websites and stuff like that for news, they are dynamically getting more and more updated. It's no longer static information. So that's yet another example where both the social network and types of things are doing. Third example really is, how do you use machine learning and data analysis to support understanding of content? Now, I have to be careful here. There's another quote I'll give you is that you can torture data to give any answer you want, which basically means is you can take an existing data set and twist it around to kind of make your representation or make your answer be very good. But what computational journalism principles say is, in addition to my analysis, I share the data with you. So you, when you see this thing, can also now look at the data and perceive it and analyze it differently. Finally, the other answer I always give is, in this current era of information, you can get information from anywhere. And again, misinformation is important. I do not know, and I'm not blaming all of you young people for this, is you folks need to be much more careful when you trust information. Because, going to unauthorized or non-authorized sources for information is very risky. So let's take the example these days with COVID. There's a lot of misinformation and disinformation. So you can go to a social media site and find out COVID information, and it's going to give you information related to what you've searched for before and basically give you your biased information continuously. What you should be doing is looking for other sources to verify that. And that's what, again, in this example where computational journalism needs to come in, provide you that, oh, by the way, this is the information we got, but there are other sources that are kind of doing it. Rather than find yourself in an echo chamber that basically says, yes, vaccination is bad, it also would say is vaccination is bad by these people, but these other people are kind of saying, no, it's not bad. And now you get to make decision by combining the information yourself, and the system should help you do this. So many examples, hopefully that answered your question.
Thank you so much for that answer. I personally thought it was really interesting. I actually personally encountered a lot of misinformation and disinformation surrounding the COVID pandemic. And a lot of people were talking about echo chambers with certain beliefs. So I think it's really interesting how computational journalism can hopefully work to combat that. Someone else here was wondering, is there any work or resources in the field of ML unique to Georgia Tech that doesn't exist at other universities?
So one basic resource is, and I'm the director of the Center for Machine Learning at Georgia Tech, and we actually have the most diverse group of people, faculty and students, because this, as you know, at Georgia Tech, we have, Georgia Tech is the largest producer of computer scientists and engineers these days in the country, so we were a big program. But at the same time, we also, besides a strong computer science program, have an engineering program, we have a sciences program, and we also have a humanities, business, and design program. The machine learning program at Georgia Tech covers all of the 6 schools. So that's why it's interdisciplinary. So we have people working with us who work on policy issues around machine learning. And then we have people working, of course, on hardware that could be doing machine learning. And then we have people working on, how would you take this and apply this to healthcare problems? And how would you apply this to being able to kind of work this out in, robots or autonomous driving? So the spectrum, the scale and the spectrum is one of the biggest strengths of Georgia Tech. I mean, we can touch almost all aspects of machine learning. That's one. The second one is we are actually working very closely to develop courseware that's available widely. So it may not be available directly to all of you because most of you are actually, unless I'm mistaken, not in college yet. But when you get to college and want to go for a master's program, we have the largest online master's in computer science program in the world right now. That allows you to get a complete master's degree without actually coming to campus, and you can do it all remotely. Just search for online master's in computer science at Georgia Tech. It has 10,000 students. And the most popular classes in that one are machine learning, AI, computer vision, computational photography, and AI types of topics. So that's one more. And the final one is working with Meta or Facebook. We're now taking those courses, making them even available not to just graduate students, but also to undergraduates and even high school students to kind of learn the basics and foundations of AI.
Definitely.
Hopefully that answers the question.
Definitely. And I think another thing that I wanted to actually ask, one of my personal questions actually, I'm wondering, so based off of that, what are some interesting problems that you personally are using AI to solve? Maybe some projects that you're working on right now or something interesting that you've worked on in the past that you would like to mention?
One of the biggest problem domains that I am really interested in and I want to work more on as much as I possibly can is using machine learning and AI to really help us solve some health related problems. And I'll give you a very interesting example. This is one of those things is, health is something that the medicine field is driven by very episodic capture of content. So, I mean, all of you are young, of course, none of you ever get sick because, you people are made out of metal and iron and, that kind of stuff. But once in a while, when you do get sick, you go to a doctor and the doctor asks you, 10 questions, and then they measure blood pressure. And I don't know if you've taken your parents or family members and stuff like that. And then, I admire doctors, but then their sort of black heart comes in and they can actually kind of think through their head, oh, this is the blood pressure measurement and stuff like that. Oh, here is a medication I can give you. Imagine if this was no longer episodic based on Q&A that they're asking you right at the doctor's office, but when you walk in, and I wear various types of sensors in my arms, and they can just download that information and get a little bit much more longitudinal information about what's going on. I mean, very classic example I tell everybody, and again, those doctors are amazing people, by the way. I'm not going at all say that we want to replace those doctors by a human robot that will actually do their diagnostics. I'm just talking about giving them more access to data. So for example, when you feel a cold and you start coughing and you want to make an appointment with the doctor, you sit in a car and you turn the air conditioning on. And when you turn the air conditioner, the cold air actually helps you. And by the time you get to the doctor, your cough is not as croupy as it was before. So that episodic types of things did not capture when you were really sick. Of course, doctors are really good at that kind of stuff. But having said that, how do you capture this kind of stuff? Now, not relevant for young people like all of you, but imagine if this kind of thought process could be applied for understanding more longitudinal data for people with other types of illnesses. And we've worked on this kind of stuff before. I mean, I've done projects on understanding people's recovery times from chemotherapy, also understanding things about how their physical activities over time change, because as you get older, you don't go out for walks as much. Or even in my case, my knees hurt now because I do various types of things. How do you actually watch over and kind of start providing guidance, saying maybe you shouldn't be doing this, or you should be exercising of this type of stuff to build your strength and difference. So that's one of the areas that I'm very interested in. There are lots of other areas. I'm very interested in making it easy for people to create high quality, informative, and useful content. I mean, one of my biggest challenge right now is that there's a whole lot of bad content out there. How do you actually support content creation of high quality and also do what I talked about is provide information that has high quality measures associated with it. So when I say something, it also finds all of the counter examples of it and says, oh, this is what this question was. What are the variations on this one? Many different ideas. And as I said, and each time, as I said, it's finding a student who wants to work on it and then letting them do it and get out of the way.
Definitely. Thank you so much for that. I find it really interesting how so many people wear Apple Watches, but I haven't even thought that doctors could maybe use that information and do things a lot more efficiently. So someone was asking, I'm not sure if I personally understand this question, but they asked, there are frequentist inference invasion approaches in stats by 2 of the 5 tribes being analogizers and Bayesians. Did you mean these 2 approaches?
So, I mean, that was more of a just touching the topic. I mean, there's a whole lot of depth and details and this kind of stuff going in there. But I mean, again, I mean, I mean, I'm one of those people who does not believe that you need to start off with one topic and, every problem is not a nail and you have a hammer. I believe in finding a new hammer for a new nail. So while I did categorize those 4 categories, and there is actually strength in each and every one of them, the question comes up is finding the right category for the problem you want to solve. And sometimes, and this is where, as I said, if you want a well-defined controlled solution, symbolic or Bayesian approaches are really good because you know exactly what decision it's going to make. But when you are actually looking at large amounts of data, the connectionist models are really good. But the problem with connectionist models are they're black boxes. You don't know how the decision was made. So explaining that kind of stuff is important, which is hard. And I'll give you an example that, if you're really kind of looking and you give, I'll give you an example that's very well known is, let's say if you give data from Netflix about movie watching to a machine learning algorithm and you don't slice it very well according to regions and stuff like that, it might start kind of wavering and biasing it a little bit. And you would not understand what the biases are until you start kind of looking at it with certain sets of newer contextualization that comes from other tools. And that would help you explain it. So how do you kind of look at data and the outputs by a combination of those tribes is important.
Definitely. And I think, unfortunately, our time is coming to a close, but I just wanted to ask one last question that I think is popping up a lot in the Q&A section. And I think it's a really unique question, especially for the audience we have here today, right? So we have some people asking, we have one anonymous person mentioning that they are a rising 6th grader, and they're actually interested in AI, computer vision, and other various topics. So they're asking if you have any suggestions on how they could start learning. And we also have people asking questions about, are there any prerequisites to learning AI? Or if you want to start and understand AI better, are there any computer languages that are good to master? So I suppose just to compose this question into one would be, what is your advice for students interested in getting into AI? Where do you suggest they get started?
So the best way to get started is, and again, hopefully this is not aimed to scare anybody else, is a lot of AI, machine learning, robotics, computer vision is all driven by math. So, dive deeper into a lot of STEM types of efforts. Sometimes people will tell you that, oh, calculus is more important than statistics. No, both of them are important, statistics and calculus. So diving deeper into some of the basic STEM fields. I mean, if anything, good thing that has happened with AI has brought more diverse groups of people to engage in STEM fields. And I think that's a good thing. And I think I would recommend everybody who is interested in this kind of stuff. Once you get into that kind of stuff, and I know several people, when I say this kind of stuff and look at me and say, I hate math. Well, you just haven't had a good teacher yet. So keep trying and you'll find one good teacher. And everybody is good at this kind of stuff. And once you find that good teacher, and also kind of sometimes invert the problem. That is, don't learn things just because there is a tool that you need to learn. Learn it why and what is the output of various types of things. So, many times people have been told, oh, learn this kind of algebra and geometry. But it would be great if you understood why this geometry is relevant to solving problems you want to do. And if AI is the problem you want to solve, invert the problem from that, saying, I want to build intelligent systems that can do inference, look at data, sensory data, and stuff like that, and use that to make decisions. Then use that to understand is, okay, what math do I need to make those decisions from this data? So invert the problem and kind of come back and then go other ways back towards trying to understand how the problem is solved.
Definitely. And I think, speaking of brilliant teachers who make you love learning, I think, Dr. Essa, you're one of those people, especially for artificial intelligence. So many thanks for the brilliant talk. And personally, I learned a lot, and I'm sure our audience did as well. If we weren't able to get to your question, Dr. Essa, do you think there's any way for students who have more questions to ask you?
You can collect them and share them with me, and I'll try
Good.
to respond to them. I mean, I would say you can, each individual can email them to me, but I think that won't scale.
Yes.
Because honestly, I'll tell you, I get a lot of email, and some of it is from those bots that I don't trust. Now, I'm not saying you folks are bots, but collect them if you can and share with me, and I'll see what I can do to respond. I mean, feel free to email me, and I try to respond to emails, but as I said, these days I get so much email that it's hard to keep up. But importantly, I mean, as I said, I'm not the only authority in the field of AI and machine learning. There are lots of experts out there. Find them close to you, and engage. I mean, you folks are an interesting group of people that are getting engaged with this very early in your careers, and use that as a foundation, and reach out and engage as much as you possibly can. Curiosity is an important part of it, and then trying to solve problems to that curiosity and learning is an essential part of it. So just keep doing that.
Definitely. And I think for those, unfortunately, since we're running out of time, for those who do have other questions that they want to still ask Dr. Essa, feel free to email the Youth AI Lab email that I just dropped in the chat, youthailab@gmail.com. And so that way you can email your questions to me, and I will compile them and send them to Dr. Essa. And then I'll also send them back to you guys, of course. So definitely, and for those who are interested in listening to other brilliant speakers like Dr. Essa, feel free to become a member at youthailab.org, which I will also put in the chat, to hear announcements for other upcoming events like this one. And of course, also announcements for resources as well, and all for high schoolers interested in AI. And for those who miss our talks, we'll also release a webinar summary after the talk, which you will also see posted on our website. So definitely, thank you everyone for coming today. Dr. Essa, thank you so much for taking time out of your Friday evening to come speak to our audience. Everyone, I'm sure, thoroughly enjoyed your talk. It was fantastic. Thank you.
No, thank you so much. I'm concerned that all of you are listening to me and not having a good Friday night, but hopefully you will get to that soon.
Definitely. I'm sure that this is also everyone's way of having a good Friday night. So thank you, everyone. Of course, if you have any other questions, I linked the Youth AI Lab email in the account. You can also find that on our website. So if the Zoom meeting ends and you don't have that, don't be afraid. And our website is also in the chat for those who are interested in hearing future news about other talks like this one. Thank you, everyone, for coming, and I hope everyone has a fantastic rest of their evening. Thank you, Dr. Essa, again, for the fantastic talk. Really appreciate it.
All right. Good luck. Bye-bye.
Thank you.
Thanks, everyone.